And we are now recording. So first thing I need to talk about is the calendar. So while I'm getting this set up, I've decided to move the test date 1 week back, okay, because I thought it'd be too much of a rush to have it, especially since we don't have class next Thursday. So it'll be the week after. And I'll show you that as soon as I can get the shared screen going here. Okay, so next Thursday, there's no class. It's a flex day. All right, so here's the adjusted calendar. We are here. I'm doing 4.7. So originally the exam 4 was going to be on Friday the 23rd. Okay, I thought it might be a little bit too much of a rush since we lost a day on the 22nd. Not that I'm against it, but because we don't have it, I feel I'm moving the test date back. Okay, so let's move the test to Friday the 30th now. Exam 4 will be there, which means I'm swapping the quiz and the test essentially. Okay, however, it does mean that I will get started with this. In all likelihood, I will do 4.9 and maybe even some of 5.1, which will not be on that test, but you are getting that ahead of time. All right. I mean, I guess if it wasn't for the idea that I want to give you the test on Friday in general, the ideal day to give you the test would have been, let's say, Monday, the 26th, or Tuesday, the 27th. But I don't think most of you like that. I'm guessing you like the idea, and I like the idea of having the test, on Friday, so I have the weekend to grade it, and you don't have to worry about it anymore. Okay, so again, we're swapping the dates of the quiz and the test, but not anything else. Okay, so again, the test only covers up to 4.8. I might finish 4.8 here. If that's the case, I'll just go on 4.9, 5.1, whatever. But the exam is now back to Friday the 30th. It will just cover 4.1 to 4.8. In all likelihood, I will start 4.9 and maybe even some of 5.1 before the test, but the test would just be 4.1 to 4.8, okay? All right. So calendar-wise, we are now up to 4.7. Whoops, I should say. Originally, I had 4.6. We're not doing any 4.6, so I'm doing 4.7. Now, I got some requests to do previous problems too, so I might be jumping back and forth between sections. Okay, so I might jump all the way back to 4.2, 4.3, and so on, since I had requests for those. So I may not stay on 4.7. Basically, I'm going to be bouncing around quite a bit. Even within 4.7, I'll be bouncing around. So I won't be going in numerical order. I might be going in difficulty order, but you might see me bounce back between 4.2, 4.3, and so on, because some people had questions about those. Okay. Mention quickly, somebody mentioned in the chat yesterday, I think involving 29, where did the 1 and 2 come in, I think was the question. So we got over here, x is plus or minus 1 for question 29. The question was, where did the 2 and negative 2 come in? So I plug in 1. All right, put 1 here and 1 here. 1 minus 3 times cube root of 1 is 1. 1 minus 3 is negative 2. So 1 comma negative 2. And when you plug in negative 1, you get 2. Okay. In class, I just said because we have origin symmetry, we have symmetry with respect to the origin, which means 1, negative 2 automatically gives you negative 1, 2. Or if you want to plug in, put negative 1 here and negative 1 here. The cube root of negative 1 is negative 1. Negative 1 times negative 3 is positive 3. Negative 1 plus 3 is 2. Okay, so short answer. I think this answers the person's question. When you plug in 1 back here, you get negative 2. And if you plug in negative 1, you get 2. Okay, so I think I answered the question. If I didn't answer the question satisfactorily, put it in the chat again, or send me an email, or see me during office hours. Okay, so that's that. Now, what's happening in 4.7? The topic is optimization problems. Okay, they're basically word problems, page 330, involving max and min. So they're all word problems, as you can see. Read all the words. You translate it into a maximizing or minimizing problem. Okay, so the first thing I'll do is I'll show you all the questions. So from the list, we had to go from 3 to 37. Okay, so page 337. Okay, in every case, you're trying to maximize some quantity or minimize some quantity. Okay. That. Okay. And let's see. To 37 again, so some of that. Okay, I think that pretty much does it. All right, so I'll get started with some, but I might be jumping out of this section. Okay, and I won't necessarily even be going in order. Okay, so how about I'll start with 4.7, number 3. Find two positive numbers whose product is 100 and whose sum is a minimum. Okay, so the two numbers, I'll call them X and Y. They have to be positive. When you multiply them, you get 100. You want to minimize the sum. So here we go. X times Y is 100. The sum is X plus Y. You're trying to minimize that quantity. All right, so if I solve for Y, Y equals 100 over X. Put that over here. So f of X is X plus 100 over X. And that's what I'm trying to minimize. Okay, with X greater than 0 and Y also greater than 0. Just want to minimize this quantity. Oh yeah, before I forget about the quiz tomorrow. Tomorrow I was going to let you have almost the entire class period to work one good curve sketch. Okay, so as I mentioned before, I realized on your exam you only have 1 hour, so I said, okay, maybe you won't be able to do a problem in its entirety. Okay, but I can do that for a quiz. Okay, so tomorrow you'll have just about the entire class period to do just one curve sketch, where I'll give you one function, you do the whole works in your group. Okay, so you know the domain, intercept, symmetry, asymptotes, intervals of increase and decrease, maximum, minimum, concave up, concave down, inflection points, and then sketch the graph. Okay, so it is a kind of problem I probably wouldn't ask you for the whole thing on an exam, but I want you to be able to show me that you can do one entire problem. Okay, lest there's anybody that says, oh, he's not going to ask us the whole thing on an exam, which might be right. So I'm never going to study it. Well, I can ask you that for a quiz. Okay, but it might take up the entire class period for that. So be prepared tomorrow for just about the entire class period where you'll get just one curve sketch problem, but you have to do everything. Okay. So that would be stuff like section 4.5, similar to that thing. Okay. All right, so anyway, X plus 100, X at a -1. I'm trying to minimize that quantity. Okay, so the first derivative is 1 minus 100 X at a -2. Second derivative is 200 X at a -3, which is 200 over X cubed. That's going to be greater than 0 for all X greater than 0. Okay, we're only allowed to have positive X and Y. If I plug in a positive, this expression is positive. Positive second derivative means concave up, which means I will have a minimum. Okay, and by the way, this is part of the proof to show me that you do indeed have either a maximum or a minimum. I definitely will have a minimum. Okay, so I set the first derivative equal to 0. So 1 minus 100 over X squared, that's what that is. Set it equal to 0. Multiply both sides by X squared. X squared minus 100 equals 0. Move over the 100. X squared is 100, take the square root, ignore the negative root. X is 10. Plug back in for Y. Y is 100 over 10, which is also 10. Okay, so the two numbers that I want are 10 and 10. Okay, the problem's finished, but a side note, what is the sum of 10 and 10? 20. Okay, if you take any other combination of the infinitely many possibilities where the two numbers have a product of 100, when you multiply them, get 100, you get something bigger than 20. For example, 20 times 5, right, is 100. What's 20 plus 5? 25. It's bigger. Okay, how about 2 times 50 is 100? But what's 2 plus 50? 52. It's bigger than 10 plus 10, which is 20. You can even have 100 times 1, which is 100, but 100 plus 1 is 101, bigger than 20. Okay, so out of all the infinitely many possibilities of two positive numbers that have a product of 100, if I want to minimize the sum, I should pick 10 and 10. Okay, that's all. Okay, so what happened? I solved for y. I'm trying to minimize x plus y. I don't want two variables. I just want a single variable. Okay. Now that I know that y is 100 over x, I put that over here, and then I get the ball rolling. I start doing my first derivative, second derivative, and so on. Okay. All right. 7. Find the dimensions of a rectangle with perimeter 100 meters whose area is as large as possible. All right, so notice for number 3, you were trying to minimize something. Number 7, you want to maximize something. You want to maximize the area. Okay, so you have a rectangle, the perimeter is 100, and you want the area to be as big as possible. That makes sense. Maybe you're growing something in your garden, or you're raising animals on a farm. Okay, you only have 100 meters perimeter. Let's say that's fencing. How do I shape it so I get as much area as possible? Okay, so here's the picture. Perimeter is 100. X by y. The perimeter of a rectangle is 2x plus 2y. That's equal to 100. What am I trying to maximize? The area, which is x times y. Okay, so I got to get down to a single variable. I don't want x and y. I just want a single letter like x. So what you do is solve for one variable. Normally, you solve for the variable that isn't x. Okay, you could solve for the other variable for x, but normally we like doing our algebra with x. So solve for y. That's easy. Y is 100 minus 2x divided by 2. Right, from here, subtract 2x, divide by 2. So this is y, 50 minus x. Okay, put that over here, so I get it down to just a single variable. So my area function, a of x, is x times 50 minus x, 50x minus x squared. Okay. Most of these problems are like this. At the beginning, you have two variables. Try to get it down to just a single variable based on some other condition in the problem. All right, so I want to maximize this quantity with x greater than 0, 50x minus x squared. So first derivative, 50 minus 2x. Second derivative, negative 2. Negative 2 is less than 0, which means concave down, upside down shape, which means when I have a horizontal tangent, slope of 0, I will have a maximum. Am I looking for a maximum? Yes, I am. And normally, they won't trick you, and I won't trick you. If you're looking for a maximum, it'll be a maximum. If you're looking for a minimum, it will be a minimum. But you have to prove it. Normally, for these problems, it's easy to do the second derivative test to prove maximum and minimum. So I definitely have a maximum. All right, so I just set the first derivative equal to 0. 50 minus 2x equals 0. Simple algebra, x is 25. Plug in 25 for y, 50 minus 25, and y is also 25. So the shape should be a square, 25 meters by 25 meters. All right, so what we're saying is you have to have a, if you have to have a rectangle, the way I should shape it for a given fixed perimeter to get the maximum amount of area is to make it into a square. Measure my guess from over here. Okay, so that's that one. Now I'm actually going to digress and go back to a previous section. So let me show you 4.7 again here. Okay, so that's that. Okay, I'm going to go all the way back to 4.1. It's 57, so let me show you that. So I'm sorry if I'm going out of order, but sometimes I get requests to do certain problems. Make sure I get the right problem. Yeah, so this is way back in 4.157. Yeah, so find the absolute max and absolute min on a given interval. So we're between 0 and pi over 2. Okay, so remember you have to plug in the endpoints. So f prime of t is -2 sine t plus sine 2t derivative is cosine 2t times 2. I set that equal to 0. Okay, normally you don't want to mix up a double angle with a single angle, so I use an identity. Cosine of 2t is cosine squared t minus sine squared t. All right, then I distribute -2 sine t plus 2 cosine squared t minus 2 sine squared t. Okay, so I've got sine and cosine mixed up. You only want one trig function. Normally when you have something like this, the majority wins, right? I can either change sine to cosine or change cosine to sine, but two of them are already sine, so there's less work to change this one to sine. So then my equation only has sine. Okay, so cosine squared is 1 minus sine squared t. So -2 sine t plus 2 parentheses 1 minus sine squared t minus 2 sine squared t equals 0. Distribute, that stays the same. That's 2 minus 2 sine squared of t minus 2 sine squared of t. These two give me a -4 sine squared of t, and then -2 sine t plus 2 equals 0. Factor out the -2. So I have 2 sine squared t plus sine t minus 1 equals 0. And this factors into 2 sine t minus 1 sine t plus 1 equals 0. Okay, so that means either this is 0, impossible, -2 equals 0, you can't do that. Okay, what makes this 0? Well, if sine of t is a half, what makes this 0? Sine of t is -1. Okay, so sine of what nice angle, first quadrant angle is a half, that's pi over 6. Sine of what angle is -1? That's down here at 3 pi over 2, but the original problem only says stuff between 0 and pi over 2. So if I only have an angle between 0 and pi over 2, this can't happen. Okay, so now I plug in. I'll plug in the two endpoints, 0 and pi over 2, and my critical point that's within the region, pi over 6. Okay, so I plug in 0, 2 cosine 0 plus sine of 0. Cosine of 0 is 1, sine of 0 is 0, 2 plus 0 is 2. Plug in pi over 6, 2 cosine of pi over 6, that's 2 radical 3 over 2. Plug in pi over 6, sine of 2 times pi over 6 is pi over 3. Sine of pi over 3 is also radical 3 over 2. So I have 2 radical 3 over 2 plus radical 3 over 2. That's 3 radical 3 over 2. That's roughly 2.6. And then the other endpoint was pi over 2. Cosine of pi over 2 is 0. If I plug in pi over 2 here, I'm taking the sine of pi, which is also 0, 0. So I see 0, 2, and 2.6. So absolute minimum is 0, 0. Absolute maximum, you should always write the exact value whenever possible. So pi over 6, 3 radical 3 over 2. Okay, so that takes care of 4.157. Okay. And I'm going back now to 4.457. One of those. This was a section on L'Hopital's roof. 4.457, page 312. Limit x equals to 0 from the right of x raised to the radical x. So that's another one of those where you let it equal to y, and then you have to do some log stuff. So 4.457, here was the original problem. Okay, so you recall how that works. So that y equal x to the radical x, which means you're finding the limit as x equals to 0 from the right of y. Okay, take the natural log of both sides. So y equals x radical x, ln, ln. Once I have the ln, the radical x comes down. Ln y equals radical x, ln x. In order for me to do L'Hopital's rule, I need something in the denominator. So if I multiply by radical x, it's the same as dividing by 1 over radical x. Okay, and you know, in algebra, you almost never did this step. You normally went from here to here, right? You would say, oh, I'm dividing by a fraction. If I divide by a fraction, I multiply by the reciprocal. But you are allowed to go backwards. In this case, we need to go backwards so I can do L'Hopital's rule. So now limit as x approaches 0 of ln y, which ultimately I don't want. I want limit as x approaches 0 of just y, but we know what to do. We're just going to exponentiate after that. All right, so limit as x approaches 0 from the right, okay, of ln x over 1 divided by radical x. This is infinity over infinity. Okay, if you plug in 0.01, 0.001, 0.001, ln of x approaches negative infinity. That's okay, that's the infinity type. And if I plug in 0.001, this also gets big. So I can do L'Hopital's rule. When I differentiate, treat this as x to the negative a half. 1 over radical x is x to the negative a half. Okay, so by L'Hopital's rule, limit x approaches 0 from the right. Derivative of the top is 1 over x. Derivative of the bottom, which is x to the negative a half, is negative 1/2 x to the negative 3/2. Okay, x to the negative 3/2 in the bottom will come up as x to the positive 3/2. That x is going to slide down. And dividing by negative a half is the same as multiplying by negative 2. So now I have negative 2, x to the 3/2 on top, x on the bottom. I'm allowed to factor out the negative 2. So I have negative 2, limit x approaches 0 from the right of radical x. And now you can see what happens. If I plug in 0.001, this thing approaches 0. So limit as x approaches 0 from the right of ln y is equal to 0. But I really want the limit as x approaches 0 from the right of y. I have the limit as x approaches 0 from the right of ln y, so I exponentiate. That's usually the trick for these problems. Exponentiate, exponentiate. So final answer, limit as x approaches 0 from the right of y, which is limit x approaches 0 from the right of x to the radical x, is indeed 1. And that's what we were looking for over here. Okay, so that's that one. And just for fun, let's actually try that. So if I plug in a very small positive number, it should work. So let me try 0.00001 raised to the square root of 0.00001. And I guess it's not close enough yet. Okay, so what I was going to show you doesn't quite work yet. I have to get a smaller number. But anyway, that seems to be what we got. Okay, then I'm jumping back to 4.2, number 5 was asked for by a student. So that was the mean value theorem, you might recall, right? And Rowe's theorem. It's almost like we're reviewing for the test a little bit, jumping around several sections. 4.2, number 5, page 292. Verify that the function satisfies the 3 hypotheses of Rowe's theorem, then find all numbers C that satisfies the conclusion of Rowe's theorem, number 5. Okay. All right, so Rowe's theorem on -1, 3. All right, so 2x squared minus 4x minus plus 5. It's a parabola. You know, it looks like that. Whoops. That's continuous everywhere. It's differentiable everywhere. Therefore, it's continuous on the closed interval from -1 to 3, and it's differentiable on the open interval -1 to 3, which is part of the first 2 hypotheses of Rowe's theorem. Continuous on a closed interval, differentiable on an open interval. And you might recall for Rowe's theorem, the 2 endpoints have to match. Let me show you that again for Rowe's theorem. Page 287. Continuous on a closed interval, differentiable on the open interval, just do that, and then f of a equals f of b. Same height for the endpoints. Okay, so I plug in -1, I plug in 3, and I hope I get the same thing. So plug in -1, 2 times -1 squared minus 4 times -1 plus 5. -1 squared is 1, so 2 plus 4 plus 5, 11. Plug in 3 here and here. 2 times 3 squared minus 4 times 3 plus 5. 2 times 9 is 18 minus 12 plus 5. It's also 11. So everything matches. So Rowe's theorem says there is a C, there's a number between -1 and 3, such that f prime of C is equal to 0. Okay. So find it. So take the derivative. The derivative of the original is 4x minus 4. Set it equal to 0. I get x equals 1. So the c value is 1. Is that between -1 and 3? Yes, it is. Okay, so that answers that one there. Okay. Okay, so that takes care of that. And now I'm going to go back and do some more of the applied max min problems. If somebody asked about a curve sketch, I'm not sure if I'll have time for it, but we'll see. But since I'm supposed to be on 4.7, let me go ahead and do some more 4.7. Okay, number 4 was an even problem. Let me show you that one. Number 4, the sum of two positive numbers is 16. What is the smallest possible value of the sum of their squares? Translation, sum of two numbers, positive, 16. X plus y is 16. X is greater than 0. Y is greater than 0. And we want to minimize the sum of the squares. Here are the squares, and you sum them up. So I want to minimize x squared plus y squared. All right, so I have to get it down to just a single variable. Normally, the trick is to eliminate the variable that isn't x. The variable that isn't x is y. So that's easy. Y equals 16 minus x, right? Subtract x on both sides. Y equals 16 minus x. Now I plug that into here. So it becomes f of x is x squared plus y squared, and y is 16 minus x. And there's the quantity that I'm trying to minimize. X squared plus 16 minus x squared. Okay. So a lot of these word problems, you start off with two variables, get it down to a single variable, and then go from there. All right, I can multiply that all out. I don't feel like it. You probably don't feel like it either. So I'll just differentiate using that. So it looks like chain root, right? So f prime of x is 2x plus 2 times 16 minus x to the first power times -1, the derivative of the inside. Okay, clean it up, 2x. Let's see. Yeah, I distributed -1 to the 16 minus x. So it's 2 parentheses x minus 16. So now I have 2x plus 2x, 4x, minus 32. Double prime is 4. That's greater than 0. On the graph, notice we're not graphing these, but if you had a graph, you would have a concave up situation, which means I do have a minimum. Are we looking for a minimum? Yes, we are. It'll always turn out to be that you want it if you set it up the right way. Okay, so set the first derivative equal to 0. Where'd it go? My f prime was 4x minus 32. That's x equals 8. So x equals 8. That means y is also 8. So the two values are x is 8 and y is 8. But now let's answer the question. The question is, what is the smallest possible value? Question 4. What's the smallest possible value of the sum of their squares? So I just plug in. Put 8 here, 8 here, 64 plus 64, 128 is my final answer. Okay. So of course, for any word problem, you want to make sure that you answer the question. So the answer is 128. All right, and see, another even one was number 8. So let me try to show you number 8 now. Find the dimensions of a rectangle with area 1,000 meters squared, whose perimeter is as small as possible. Okay, minimize the perimeter. So here we are. We have a rectangle, x by y. It's 1,000 meters squared. So my answer is going to be in meters. Minimize the perimeter. Formula for perimeter is 2x plus 2y. Right. In order for me to minimize this, I want to get it down to a single variable. I need to get rid of y. Can you solve for y over here? Sure, divide by x. Y is 1,000 divided by x. Pick that up, plug it right in there. So my perimeter function now, p of x, is 2x plus 2y, but here's y, 1,000 over x. So that's 2,000 over x, or 2,000 x at a negative 1. So that's the quantity that I want to minimize. Minimize this quantity with x greater than 0. All right, so first derivative is 2 minus 2,000 x at a negative 2. This is better for calculus, but better for algebra is that. Double prime, derivative of 2 is 0. Derivative of this, negative 2 times negative 2,000 is a positive 4,000 x at a negative 3, which is the same thing as 4,000 over x cubed. That's always going to be greater than 0 for all x greater than 0. Right? We're only allowing for positive x. It doesn't matter what I plug in. This quantity is positive. That means I'm going to have a minimum because positive second derivative means U-shape, concave down. We're looking for a horizontal tangent, slope of 0. It'll be a minimum. Am I looking for a minimum? Yes, I am. All right, so I'll set p prime equal to 0. Set the first derivative equal to 0. So it's 2 minus 2,000 over x squared equals 0. Multiply both sides by x squared to clear the fractions. So this becomes 2x squared. That's a 2x squared. Sorry, can't see it. 2x squared. 2x squared minus 2,000 equals 0. Factor out of 2. X squared minus 1,000 equals 0. Which means either 2 is 0, which is impossible, or x squared minus 1,000 equals 0. All right, add 1,000. X squared equals 1,000. Square root. Ignore the negative. So I have radical 1,000. 1,000 is 100 times 10, and the square root of 100 is 10. So 10 radical 10. Okay. Find y. Y is 1,000 over x. So it's 1,000 over radical 1,000, which is also radical 1,000. Okay. You can rationalize the denominator, multiply top and bottom by radical 1,000. And then the 1,000 here cancels the 1,000 at the bottom. So y is also 10 radical 10. Right? So the dimensions are 10 radical 10 by 10 radical 10 meters. So again, it's a square in this particular case. Okay. And let's see, I think I'm done with that picture. So let me go ahead and give you the focus thing again. All right, so that's that. Okay, let me try to show you 15. On our list. '15, page 337. If 1,200 centimeters squared of material is available to make a box with a square base and an open top, find the largest possible volume of the box. Okay, so you have a box, the base is a square, open top, find the largest possible volume. Okay, so I drew myself a little picture of a box, square base, so x, x, but it does not say it's a cube, so this one doesn't have to be x, I just called it y. Surface area is 1,200 centimeters squared. Okay, that's the amount of material. Maybe that's cardboard, right? Take the cardboard, you're folding it up into a box. No top, but there is a bottom. So I have 1,200 centimeters squared for surface area. Maximize the volume. The volume is length times width times height. So it's x times y, or x squared y. All right, let's try to get an expression for the surface area. I have 5 surfaces. I've got the bottom, then the 4 sides, right? Front and the back, left and the right. Okay, what's the area of the bottom? x by x, x squared. The front is x times y. The back is x times y. The left and right are x times y. So I have 4 of them. So the surface area I have is 1200. 1200 equals x squared for the bottom plus 4xy. Quick timeout before going on. Suppose it asks the question that I had a top and a bottom. If there was a top and a bottom, can you see what little change it would make? Instead of x squared, 2x squared. Top and bottom are both x squared. So if it said it's a closed box, the only little change I would make is that there would be a 2 right here, but it's open. All right, solve for y. So subtract x squared, divide by 4x. So y is 1200 minus x squared divided by 4x. That mess gets plugged back in here. That way I just have a single variable. I only want one letter. So now my volume function, v of x, is x squared, parentheses, all of this stuff. 1200 minus x squared divided by 4x. Okay, and it looks like I can cancel an x. That x cancels that x. All right, so simplify it. 1200 divided by 4 is 300. I have 300x minus 1/4 x cubed. And that's what I want to maximize with x greater than 0. Okay, so again, sometimes you want to maximize a quantity. Sometimes you want to minimize a quantity. All right, so first derivative, 300 minus 3/4 x squared. Second derivative, derivative of that is 0. 2 times that is negative 3/2 x. Now, again, I'm only plugging in a positive quantity. If I plug in a positive quantity, this is going to be less than 0 for all x greater than 0, right? Negative 3/2 x. For this kind of a word problem, we only want positive quantities. If I plug in any positive number, where did it go here? Lost my place. Here we are. That's going to be negative. So negative second derivative, concave down, I have a maximum. Am I looking for a maximum? Yes, I am. Okay, so that proves I have a maximum. So set v prime, volume, equal to 0, and then I'm good. So here is my v prime, right? 300 minus 3/4 x squared equals 0. I don't like the 3/4. I'm guessing you don't either. So multiply both sides by 4/3, the reciprocal. 4/3 times 300 is 400. 4/3 cancels that 3/4, so negative x squared, and 0 times anything is 0. That looks nice. Difference of squares. 20 plus x, 20 minus x equals 0. X is negative 20, throw it out. We only want positive quantities, and x is 20. Now I got to go back and find y. Y was 1200 minus x squared divided by 4x. So 1200 minus 20 squared divided by 4 times 20. 20 squared is 400. 4 times 20 is 80. 800 divided by 80, 10. So y is 10. All right, so x is 20, y is 10. The dimensions are 20 centimeters by 20 centimeters by 10 centimeters. And the last thing I want to do is answer the question, right? So what was the original question? 14? 15. Find the largest possible volume of the box. So I want the actual volume. So 20 times 20 times 10, 4,000. Okay. And I'll set you up with 14, but I wasn't going to do it. I'll get you to a certain point. It seems similar. "14. A box with a square base and open top must have a volume of 32,000 centimeters cubed." Okay, so you have a fixed volume. You must have that much space to put, whatever, put all my stuff, put all my belongings or whatever. Find the dimensions of the box that minimize the amount of material used. So you want to minimize the surface area. That makes sense. So I have to go out and buy cardboard and fit it into a box. I want to buy as least amount of cardboard as possible because that will minimize the cost, right? So here you must have a certain amount of volume. So obviously I want to buy as little material as possible. So it's somewhat related. So here's the setup. Picture looks the same at the beginning, x by x by y. Volume is length times width times height. Has to be 32,000 centimeters cubed. So it's x squared y. Can you solve that for y? Sure, just divide by x squared. So y is 32,000 divided by x squared. Now, the formula for the surface area, same thing as this. It said open top, square base. So same thing, x squared plus 4xy, just like over here. The difference this time is that you're trying to minimize this quantity. Again, you have the bottom of x squared. The front is xy, the back is xy, the left is xy, the right is xy. So I have x squared plus 4xy. I want to minimize this quantity. So how do I write it so that I get rid of the y? I take this thing, 32,000 of x squared, put it right here. And now my expression only involves x. I don't have any more y. So a of x is x squared plus 4xy. Here's my y. And it looks like I can cancel an x, right? That x can cancel that x. And 4 times 32,000 is 128,000. So x squared plus 128,000 over x. And that's what you're trying to minimize with x greater than 0. Okay, so I'll just say, et cetera. You get to finish the rest of that on your own. And of course, if you're going to differentiate, make that 128,000 x to the negative 1. So that's what I meant by that. Bring that upstairs, make it x to the negative 1. Okay, so let me do my focusing thing again here for 15 and 14. There's all that. And that was 14. Okay, and you already saw that, so you don't have to worry about that. Okay, and let's see, we only have a few minutes left. I had a question about number 5 on the curve sketches. So I'll just talk about it a little bit. Maybe I'll talk about it a little bit more tomorrow. Again, tomorrow I'll be ready for an entire curve sketch. Okay, so a question about 4.5, number 5. X times x minus 4 cubed. Okay, so again, for tomorrow, expect almost the entire period that you'll get to do one of these things. So what will you have to analyze for the quiz? All of this stuff that I mentioned before, page 315, right? Domain, intercepts, symmetry, asymptotes, intervals of increase or decrease, max and min, concavity, and sketch. So again, if I give you a question like that on the test, it would have to be something fairly fast that you can do the whole thing. Otherwise, I might just say, okay, only do, D, E, and F or something like that, or just do max, min, and concavity, or only do domain and intercepts or whatnot. Okay, but for tomorrow, you're definitely gonna have to do the whole works. Okay. This particular problem, number 5, we're supposed to do the whole works. Obviously, I can't do that in the remaining few minutes we have, but I'll just get you started with it, and maybe I'll do more of it tomorrow or Monday. Okay, so x times x minus 4 cubed. All right, so let me just mention quickly, domain is all real numbers. It is a polynomial. So domain is all real numbers. Intercepts. What happens when you plug in x is 0, y is 0? How about y is 0? X can be 0 or 4. So domain is all real numbers, the funny looking R. Intercepts are 0, 0, and 4, 0. Is there any symmetry? I replace x with negative x, put a negative x here and a negative x here. Let's see, where'd it go? Negative x times negative x minus 4 cubed. Is that the same as the original? No, it isn't. Is it the opposite of the original? No, it isn't. So there's no symmetry. There are no asymptotes. There's a polynomial. Polynomial graphs won't have any asymptotes. Okay. It'll just shoot out to either infinity or negative infinity in the long run. Okay, the derivatives are a little bit of a bear. Okay, so let me try to set you up with the derivatives back here. So this looks like a product root. First, x times the derivative of the second, 3 times x minus 4 squared, times 1, chain root, but the derivative inside is 1, plus second function x minus 4 cubed, times the derivative of the first, which is 1. Okay, and before I take the next derivative, you want to clean that up. There's a common factor of x minus 4 squared, right? So factor out the x minus 4 squared. This would be 3x. This will have one more x minus 4. So 4x minus 4 times x minus 4 squared. Okay, so let me just do the second derivative and then I'll probably stop. I'll show you the rest, hopefully at the beginning of tomorrow, then I'll let you do the quiz. Okay, so second derivative, product root. First, 4x minus 4, times the derivative of the second, which is 2 times x minus 4, plus second function, x minus 4 squared, times the derivative of the first function, which is 4. Once again, factor out an x minus 4. There's an x minus 4 here, there's an x minus 4 here. So that comes out. If I take out an x minus 4, this still has a 2 for x minus 4. This has a 4 and another x minus 4. Okay, so I have an x minus 4, clean this up, 8x minus 8 plus 4x minus 16. That part there is 12x minus 24. Finally, factor out the 12. So 12 times x minus 4, x minus 2. Okay, and we're out of time, so that's that. Okay, so most likely for tomorrow, I'll try to spend the first few minutes finishing this up, but the vast majority of the class, a good half an hour or longer, I'm hoping to give you maybe 40 minutes to do the quiz tomorrow. You'll do an entire curve sketch. Okay. All right, so that'll do it for today. Let me quickly check the chat. Let's see. I know some of you have questions about it. I won't be able to get that. Okay. All right, some of you asked that. Thank you, Prasanna. So concave up, second derivative is positive. And yeah, and that takes care of that. All right, so that's it. So tomorrow, most of the time, I'll give you one of these curve sketches for the entire class period for the quiz. And a reminder, I'm moving back the test date. The test date is now going to be on the 30th, Friday the 30th. Okay, but again, that probably means I'll start 4.9 and 5.1. All right, that's it for today, folks. Okay, have a good day, and we'll see you next time. Okay, bye, everybody.
Professor?
Yes.
I was wondering if I could talk to you for a second, just really quickly.
Okay. Did you want to wait until everyone's else is gone? Or
yeah, it's fine. I don't mind.
Okay.
So it's about the move test date. So I have a work commitment on the 30th, and I was prepared to do class that day, but I'm not gonna really be in a great space to sit down and take a test and be in the right mindset to take a test. Is there any way that I can take it earlier?
Okay. I think we can maybe arrange something. Can you send me an email, maybe, Charlotte, and then I'll think about it.
Definitely.
Okay.
And I can take it next week. I can take it the date we were supposed to take it or the week after, and I'm ready to get ahead also.
Okay. All right. Now, please send me an email, and yeah, I'll think about it.
Thank you.
Yeah. Okay. All right. Welcome. Bye. Patricia, did you have a question?